Hello and welcome to the second half of my workshop on how to use the Health and Retirement Study. I'm Ryan Edwards. You can reach me at this email address listed on this slide if you have any questions. In the first half, we talked about what the HRS is and what's in it. That's the tell part. And in this half, I'm going to talk about the show part. How do you get access to the HRS and how do you work it? How do you access it? Well, there is no online analysis tool like there is for some other types of data sets, such as the Integrated Health Information Survey, IHIS. Also, the census data you can usually analyze online. The HRS is not like that. You have to download it and load it into a statistical program of your choice. Data files are available to registered users at this website, and I'll click this here with my Mickey Mouse hand. Here is what the HRS website looks like. There are a number of different links, lots of words, just like my own website. And to get started, I suggest what you do is click into Data Products here and click on Access to Public Data, which will require you to register yourself if you haven't already registered. So if you were to click New Users here, then it would bring you to a form I think that you get to fill out and enter your details, and you get to sign up for emails from HRS, which you may or may not want to, and some descriptions of what you want to use the data for, I guess. Since I've already done all this, I'm just going to skip through this and go back and log in as a registered user, which I am. Once you're logged in, then you can click on this Data Downloads page link, which takes you to this very lengthy list of what's available. Everything on the left-hand side of the screen are the original HRS data the data products. On the right-hand side of the screen are other things like the restricted files and the RAND contributed files. Here's where I suggest you start with HRS is by downloading the RAND HRS data file, which is in its ELF version right now. So, a bunch of words, and further down the screen, I'll just scroll down here, is where you want to go. So, for me, I like to use Stata, so I would just click on this zip file, which would download everything. The documentation, I guess even that PDF is a zip file. It's a rather large document, that's for sure. Go back to the slide. So that's the HRS website, and what you'll find up there are all the HRS core and exit interview files. The tracker file, which is something that measures the longitudinal characteristics of the data, such as mortality, and the RAND files, which I suggest you start with when you're first getting started with the data, and documentation on everything, including the restricted and sensitive files as well. Registering should be fairly straightforward, so I don't think you'll have a problem with that. Well, where should you start? Again, I think you should start with the RAND file, and I can talk about some advice you might find useful in deciphering the original HRS data releases, which you may have to resort to if you have particular questions that the RAND file does not answer. We'll talk about syntax associated with merging data sets. I'll talk about reshaping the longitudinal RAND file from wide to long in order to run a panel estimator, which you may want to do. And then we'll also look at a hands-on example using the RAND file, and I'll do it in Stata. The complexity of HRS brings upsides and downsides. It's so rich that there's a very good chance that your ideal question has been asked sometime of somebody, which is good. But the challenges are when it was asked and of whom, and figuring that out. What I suggest you do is using the online question concordance fillable search page, and I'll click through here with my Mickey Mouse hand. I love how that shows up like that. And I'll make the text bigger so we can read this. You can select, maybe if I make this even larger, it might be a little bit clearer. You can select any one of these individual data sets or click Select All down here at the bottom. And then you can also select particular interest areas if you want to narrow down your search. At the bottom of the screen here, you can type in something like chances if you're interested in, well, let's go with chance. If you're interested in the expectations variable. Now if I click Submit Query, it's going to pull up a whole bunch of results, a whole bunch of hits that have the word chance associated with them. Here, well, take chance new job is a question in the HRS 1992. We see that here on the far left, and it's in the cognition section, and I think it has to do with the risk preferences questions that are in there. The ones I like to use are these, the subjective survivorship questions, the chances of living to 85 or to 75 that were asked, say, here in 1994, and there are other versions of them later. So that is one tool you can use to get a handle on what might be in the underlying data sets if you find that the RAND file does not have what you want. So the challenge is that if you find it, are linking what you find to individuals or to households, other variables, and in particular bringing data forward or backward in the panel. If you look at the underlying data in the HRS files rather than the RAND file, you need to make sure that the don't know or refused data are coded reasonably. So they usually will show up as numerics in the primary data distributions, and you probably don't want that to happen. So the RAND file is where I think you should start. Let's have a look at that and talk about merging multiple data sets. Again, this is repeating myself a bit here. If you do need to access the original data releases and you find that the concordance doesn't answer your question, you may try looking at the original data files themselves. Sometimes the lists of variables in each data set are so darn long as to preclude easy examinations and easy analysis. And so another hint there is that what you might do is look at the dictionary files of used stata. Those list one variable per line and brief descriptions of them, which is handy. You can also keyword search the concatenated codebook text files or the questionnaire PDFs if you need to find a question that way. And again, beware of these numeric codes for don't know and refused. So suppose you then had found that the data that you want is in this H08B_R.dct file. This is the stata code that you would use to read in the data in that data file. It's described in the DCT as to where the actual text is, and what stata uses with this infile command is that DCT file to figure out where things are. If you then want to join data for individuals across this data set and the RAND data set, let's suppose, the linking variable is HHIDPN. In most of the HRS stata DCT files, these are actually read as strings. Now you could change that in the underlying DCT file if you wanted. You could also just run with it and concatenate the strings using the plus sign like this. So gen HHIDPN equals the two strings added together is a concatenation. And then what you'll need to do is destring this variable because the RAND file treats HHID as a numeric, so you can't leave them as strings. Then finally, there's the merge command there at the very bottom. You do want to make sure that your HHIDPN variable has the right precision, because if it doesn't have the right precision or the same precision, well, it needs to be the same variable, basically, the same data across these data sets. And if it's not, you're going to run into problems. And I've learned this the hard way, so try not to repeat my mistakes. Another merging mechanic or two, there are actually two others I can think of, and I'm sure there are others as well. A lot of the RAND documentation implies that they use this top formulation where what they do is destring these individual identifiers first and then create a new HHIDPN using this formula in the third line here, multiplying it by 1,000, then adding in the PN, and that certainly could work. Again, beware the precision issues, and I prefer the string concatenations. You can also merge by both of these variables if you want, but the problem with that is that the RAND file only has the one variable. So if you want to do that, you need to create HHID and then PN from the RAND file if that's what you're merging to. If you're merging to something else, you obviously don't have to worry about that. Well, the RAND file is set up in a very convenient way, but there will be some time required to get a handle on how it works, on what the variables look like and what they mean. HHIDPN is the key, it's the individual identifier. HA cohort is also a very useful variable that tracks which birth cohort the individual is assigned to. So the original HRS cohort that was aged roughly 50 to 60 in 1992 when the thing began is going to be called the HRS cohort here in this particular variable. The second character in this variable name is the letter A, and that means it's the same across all time periods as, for example, is this variable. So the birth year for a respondent never changes, and as a result, the variable name is RA for all years, B year. You also see this in the sex of the respondent, which presumably doesn't change. It could, theoretically, but I guess it doesn't, or at least my guess would be that people are not asked that twice, ever. I don't know. The respondent's education in years also never changes, and of course that most definitely could change, although it's less likely to do so for people over age 50, but it could. I've thought that perhaps HRS should try to ask this more, or get educational histories or something, and they haven't yet. There's another categorical variable that measures the educational attainment in terms of high school versus college versus further, that kind of thing as well. This particular one measures the years of education, which economists tend to like. The IW stat variable for respondents, with now the uppercase K in the second character position here, measures the interview status in wave K. This varies, of course, across waves. An individual could not exist yet in the, well, they exist obviously, but they're not in the survey yet. In early waves, perhaps. They might also not be in all the waves because of some reason, maybe they're out of the country or something. They might also have died. And so that variable measures the mortality along with other things. NWK is a binary indicator of whether or not the respondent is actually measured in the wave. Gender of the spouse can vary because people can divorce and remarry. And so SK gender then would be, say, S1 gender, S2 gender. It's the gender of the spouse in each of those waves, and that can be different. This is also true about the years of education for the spouse. Well, if you want to reshape the data to examine them in a panel framework, this is what you might do. Originally, the wide format is what the data sits in as it comes out of the RAND file, and here, for example, might be a visual comparison of how things look. There's one individual in the first row. There's one individual per row. So the first one is HHID 1010, and that individual has self-rated health status. That's what SHLT is. The subjective self-reported health status on a 1 to 5 scale. And they have a value of 2 for that in the first wave, a value of 3 for that in the second wave, and a value of 4 for that in the third wave. There's another individual 1 row down, and you can see different health dynamics there for that person. Each individual gets a single row, and for longitudinal analysis, you often want a long format. Each row becomes a person wave, and the way to do that would be, for example, with this code in Stata, where I've dropped all the other variables. You need to do that, or tell Stata which variables go where, whether they're all getting reshaped into columns, rows I guess I should say, or if they're constant across individuals. So the argument to the I option here needs to be the variables that are constant for individuals. In this case, it's HHIDPN. And the J argument calls or creates a new variable called wave, as you'll see in a second here. In the long version of the data, the wave variable is generated anew, and it is equal to this particular number that takes the place of the @ sign in our @ SHLT, or the one line above that, the asterisk there. So that's how to reshape, and my thanks to my graduate student Alice Ukarnan for pointing that out, that the @ sign works that way. It's kind of a handy trick to be able to know. And you know, these things are stuff you learn with repetition and application. Here's an application I worked up just for this this workshop. The question you might wonder about is, does smoking worsen health? If you're a social scientist anyway, because don't we all know that in fact it does worsen your health? Yes, I believe that it's bad for you, so please don't take any of this that I'm about to show you too seriously in terms of the topics. Like saying kids Don't smoke, just like I like telling my undergraduates to stay in school. Don't do drugs, stay in school, and don't smoke. Well, let's think about using this particular question to explore the RAND HRS files. We want to examine this relationship where the little x is smoking. It's going to be a binary variable. The little y on the left-hand side is self-reported health. That's the outcome or endogenous variable. And the big X contains various controls that we might think are useful. In HRS and many other surveys, self-reported health is actually on an inverted scale, which can kind of trip you up if you're not careful. So a 1 is the code for excellent health, 2 is very good, 3 is good, 4 is fair, and 5 is poor. So when little y gets bigger, that's not an improvement in health, that's just the reverse. The health actually falls when y is bigger, so you have to kind of turn this around in your head. Smoking is bad for your health with this measure if the partial derivative here, the beta, I should have written that in here, if beta is actually positive, which is, again, counterintuitive. And that's just the way we do it as health economists. With the HRS, you can either estimate equation 1 with ordinary least squares. You could also do it theoretically with instrumental variables by linking in something that's exogenous to the individual's choices, such as cigarette prices. And you could do that with state or even more micro level geocodes. We're not going to do that today. That's restricted data that I don't have. And it's just good to keep in mind that this is possible. The other thing, though, that you can do today is estimate this with a panel estimator of some variety. Ordinary least squares is likely to be biased by omitted variables when we don't have the right big X's, when we don't have the right controls. You can obviously imagine that there are X's that we don't know about that affect health and the decision to smoke. And so if we don't control for those correctly, then we might end up in omitted variable bias land, and that would not be good. Another big problem is that there might be reverse causality. We might have gotten the Y's and the X's reversed, and that's another big problem. A good instrumental variable, like cigarette prices, is probably, well, at least to economists, is probably the preferred method of trying to unravel this problem. Another thing might be a natural experiment, such as a cigarette shortage or something like that. I can't imagine anything like that has ever happened in recent times, but I suppose back in the day, when distributions were not so worldwide, there might have been a fire at the cigarette factory and everybody, smoked at that point, but then they didn't have any more cigarettes to smoke afterward, and that might identify some effect of not smoking on health, for example. Well, all that aside, panel fixed effects are the thing that's feasible right now. You could also do panel random effects, and I don't have anything to say about that in these slides, but it's an interesting question, and you can test for whether one or the other does a better job of modeling things. They are interesting because they reveal the relationship between differences in X's and differences in Y's. They don't isolate the causality problem or solve it, but they're an interesting perspective, and mechanically it's a neat thing to be able to do with Stata. So the key variables here, we've already talked about HHIDPN and RA gender, but they also include RA race M probably. We might want to control for race when we're measuring or modeling that as health. Ethnicity also is something that's legitimately in a health regression. Age, of course, health tends to decrease with age. I'm going to put this in linearly, and that may or may not be right. You could put it in with categoricals or with polynomial or something like that. And here I should have mentioned this earlier, but the RKSHLT is the self-reported health status on a 1 to 5 Likert scale that's asked every wave of individuals. That's going to be the key endogenous variable, the left-hand side variable. The key right-hand side variable will be the 0-1 binary indicator of report smoking now. And then education arguably also belongs in a health regression, so we're going to use that as well. Well, here is a whole bunch of commands, and what I'm going to do is just put them up here so that they're in the slide. I don't expect you to be able to read these very quickly, and I'll go through them one by one in Stata in just 1 second. I think I'm going to end in Stata, so let me also just put up this slide. Here are some references with hyperlinks that are relevant for this and the part 1 of the workshop talk. And now let me switch over to Stata. Okay. Here are the commands in the do file editor, and what I'm going to do is select each and run them. First, the data file needs to get loaded in. It's a fairly large data file, about, I believe, 420 megs or something. 427 megs it looks like. And this was a suggestion in the workshop to just list the data set in a few elements. I guess the only problem with that here is that, of course, there are so darn many variables that it's a little difficult to see. So maybe what I'll do instead is list HHIDPN, RA gender, and R smoke N, and R SHLT, and list those in the first 10. Well, even there we've got a whole bunch of observations per individual. Here's a male, HHIDPN 1010, smoking in the first wave, not smoking in the second, and then not appearing in the rest, and so that individual may have attrited or may have died. Here's a female who smokes all the time in the sample up to the 6th wave and then isn't in the sample anymore. Just out of curiosity, you get the drift here. Let's now list another variable along with this, the RIW stat, and let's look at the second. Let's see, yeah, so here we can see in this cell right here that by the 6th wave this individual has died. This might be interesting to look at up here too. Yeah, as I suspected, both of these people died. This male stopped smoking by the 2nd wave and then was dead by the 3rd. This female smoked the whole time and then was dead by the 6th. So, going back to our example, let me now just keep this subset of variables that I decided to look at. And first, let's run an ordinary least squares regression. This last bit of code, after the comma VCE robust, is commonly seen in do files by applied microeconomists. It's heteroscedasticity robust standard errors, I believe, and you may or may not wish to duplicate that, but I thought I'd toss that in there as a little hint about what some other researchers like to do. So here are the results. Here's the command at the top, the regression. So REG is an ordinary least squares regression of this. The first entry is the Y variable on the rest of things. So self-reported health status in wave 10, on smoking in wave 10, and then a whole bunch of indicator things. I dot something gives you an interaction term for each of the different categorical values of that particular variable. So here what's happening is that females are those for whom RA gender is equal to 2, and so they get a negative coefficient. It's not statistically significant over here, but it is negative. The main thing that we're going to compare is this part in the very beginning, whether or not the coefficient on smoking is positive or negative. And here it's positive in the ordinary least squares regression. Smoking is bad for your health. It raises this self-reported index of health, which means that health is deteriorating with smoking. Some other interesting things that turned out here is that we're controlling for education and age and race, and Hispanic ethnicity is actually associated with worsened health as well. And I think that was a little bit surprising to me because of the Hispanic paradox. It's more consistent with what you might expect to see, given that Hispanics are also have lower socioeconomic status on average. We're not controlling for income here, which might give us some interplay then with Hispanic status. They look more like the race group minorities, which are, in the case of the 2 group, that's African Americans, 3 are all others that are not white, and both of them have a self-reported health status penalty as well. So that's the ordinary least squares result. Now I'm going to drop the education years, and I just did that to make sure that all the code shows up here. I don't have to do that. But when I run fixed effects, which I'm going to in a second, you can't, or well, you can, you won't be able to actually include education because it stays constant over time. And when you run panel fixed effects, all of the things that are constant for the individual over time in the panel get washed out. This is the reshape command, which is the crucial one for moving us between wide and long. And so let me just list the data set now in 1 to 10. And you can see here we've got the new wave variable that's created for this individual over time. Having reshaped, let's now run a pooled regression. So all this is doing is running ordinary least squares on the pooled data. It's not using any of the panel information yet. And what you can see is that the main result is the same basically as it was in the individual regression in wave 10. Here what we're doing is adding in observations from waves 9, 8, 7, etc. all the way back to 1 in a very similar way. Individuals are duplicated here. We're not taking account of that yet. And what we find is that this cross-sectional result is upheld here, that smoking reduces health by a fairly large amount. Well, you might wonder whether that's going to hold up in a fixed effects regression, which looks at the differences in smoking compared to the differences in health for an individual over time. In order to run XTReg, which is the fixed effects or random effects, it's a cross-sectional time series is where XT comes from. I've got to first set the tset variable, or that is call tset with HHID and PN, HHID, PN, and wave. Those are the two arguments to the tset command. And they set Stata up to actually run the panel analysis. That's important for this next command, which is the fixed effects ordinary least squares regression. So it's just running linear regression, but we have individual fixed effects which are signaled by this last FE after the comma. And if I do that, it takes a while, because what's happening is Stata is estimating a different fixed effect for each individual in the sample, and there are a lot of them, something like 30,000. That's this number that shows up here in the results window, about 30,000 individuals, and that's a lot of fixed effects. Well, what do we see? Well, you might have guessed that because I was going to show you this, it's interesting. The coefficient is actually negative and statistically significant. What this is telling us is that changes in smoking behavior seem to produce the opposite effect. Well, produce is probably the wrong word, but they seem to produce the opposite effect that we might expect. People who start smoking report better health. People who stop smoking report worse health. And I'm not saying that this is evidence of any kind of causal link at all. It certainly is far from that. I think it, to me, suggests that people who stop smoking might become rather unhappy. They might also gain weight, it's sometimes said. People who start smoking again might be happier because they're smoking again. And as a result, the happiness, the mental health part is probably an element of self-reported health status in addition to the physical health. And it also could be the case that there's something else funky going on with how smoking relates to physical health, which is also measured in that index. So I don't mean for this to be anything other than what it is, which is an example of how to use the HRS data in Stata. Please don't take it literally. If you like, look at the references, see if there's any discussion of smoking in there. If there is, they'll probably would have a very different perspective on things. And thank you. Thank you for this. I hope this was helpful, and please email me with any questions.